And it's a very great pleasure to be here today. I'd like to thank the organization for what until now at least seems a perfectly organized conference. And I'm very happy that and grateful that they invited me to also give a lecture here and to share some recent results, which are actually the results of two PhD students that very recently, so in the last month, defended their thesis, so Suzanne Schoenmaker and Oscar Brandt-Korstius. And I'll be talking about something else than I've been usually talking about in the past year. So I normally was talking about CO2 hydrogenation, so I decided to do something about a different reaction, which is bimetallic catalysts for hydrogenation and dehydrogenation reactions. And I specifically would like to look at particle size effects and composition effects. But this is the catalyst preparation session, so I decided to insert at least a few slides also about catalyst preparation. Catalyst preparation can be very nicely controlled and very complicated, and that's what you see, for instance, here. For you could use a physical deposition technique, you can use colloidal techniques, but in our group we're usually specialized in techniques that are also used on a large scale in industry, like precipitation and impregnation, and we try with these tools to nevertheless have some control over the particle size and the particle composition. And this is two things that I'll be talking about today. So if you have this, I would say, rather primitive techniques like impregnation, where you just take a liquid with a salt which is dissolved, you take a porous support, you impregnate, you heat, and you nevertheless would like to have a well-defined catalyst, it's quite challenging to have control over the particle size. And it's also quite challenging to have really composition control. So I put here two of the methods that are usually used when you're trying to tune the particle size, and they almost always work. And these are simple methods, like if I would like to have a bigger particle, I just increase the amount of metal that I put. So you see here an example for copper or copper oxide, where simply on a nanoporous silica support, we've used a copper nitrate solution, and we just put more and more copper, so we just make the solution more concentrated. And what you see typically is that then indeed also the particle size grows. Just because within your porous structure on a given surface area, you're putting more metal, and hence you'll have a larger particle. And another rather crude way of doing things is also to change, for instance, the pore size. And this is another way of just making sure that you have more of the metal around and that you hence get larger particles. So here you see some experiments where we just varied the pore size of the silica, and we put the same concentration of precursor solution. And also then when you have larger pores, you'll have larger particles. So these are some methods that almost always work, but they do have some disadvantages. And one of the big disadvantages is that you're not just tuning the particle size, you're also tuning your weight loading or your support properties. You could also choose a totally different precursor, but also then you're changing a little bit the chemistry of your system. So are there also ways to try to tune the particle size without changing very important other parameters? Well, this is possible, but then you really need to understand your system well. And it's not one size fits all. You basically really have to look then at the metal and the support and the precursor and how you could tweak it in such a way that you can vary the particle size without varying anything else. And we did this for a few selected systems, but it takes a lot of time and effort to understand really well for a given system how to do this. So this is an example of just impregnation with nickel nitrate. And it looks very simple because you just bring a precursor solution and a support into contact and you do some heating, and you might have nicely defined very small metal nanoparticles. But almost dream on, because you really need to really control all the steps very well, because there's very complicated chemistry going on during the decomposition of these precursors. And the next speaker in this session is also going to go into a bit more detail there. But if you understand the system well, and if you can, for instance, tweak the heat treatment, which might be the duration, but it might be also the ramp, it might be some complicated temperature steps, or for instance, the atmosphere in which you do these heat treatment steps. It might allow you, even starting from exactly the same precursor solution and support, by just varying some of the heat treatment or gas atmosphere, might help you to also tweak the particle size. And then you have a wonderful set of catalysts, because they have a different particle size and everything else is the same. So in this presentation, I'm going to give two examples in much more detail, and both of them actually I'm using carbon supports. And carbon supports are one of my recent favorites, I would say. Also for the preparation, because with carbon supports you can tune the surface chemistry. You can make them acidic, you can make them alkaline, you can put a high density of surface groups with oxygen or with nitrogen, and this helps you also in the preparation to tweak things like the particle size. While very often during reaction conditions, if they're a bit more harsh, your functional groups will actually be gone. So it's just to help the preparation as well. Another reason why I like them is that you really can look at particle size effects, and they're almost freestanding particles. So they have a relatively weak interaction with the graphite support or carbon support or graphene support, which means that you can really study also intrinsical particle size effects. Also, when you add another component, like a bimetallic or a promoter, on a weakly interacting carbon support, very often this second component will go to the metal particle. So you do not have a lot of spectator species that are just spread around the support, but they will be on the active side of your metal particle. And last but not least, it also facilitates characterization. And you'll see my presentation quite some electron microscopy, for instance, but I also very much like X-ray absorption spectroscopy. And the light weight of a carbon support helps to get a very good signal to noise or to background ratio. So one of the other techniques that I really started to like very much recently is to start from a very well dispersed metal phase. So there are a lot of wonderful talks here about single atom catalysts. I'm not using them as single atom catalysts, but I'm using them to prepare larger particles. But for instance, just starting from copper nitrate and having a heavily functionalized carbon support, we can spread the copper, we can disperse it in single copper species. I mean, it's not an atom, it's an ion, but we can disperse them in single species over the support. And then if you do controlled heating, actually these particles will be reduced from copper 2 plus to copper plus to zero valent copper. And also they will very gradually grow. So we follow this with X-ray absorption spectroscopy. You can follow the growth of these particles. You can follow the growth in the coordination number. And you can stop at any moment in this process at the particle size that you'd like to have. So I use this also as a tool just to make a series of catalysts with different particle sizes, again, without changing anything else. So the precursor is the same, the loading is the same. In this case, it's 9 weight% of copper, and also the support is the same. And I'm going to give two specific examples in this presentation, and one is of palladium, and this palladium has been grown by this method. So we do a simple incipient wetness impregnation. The drying is extremely important. The drying phase, when you do impregnation, the drying phase is also very often where things retract due to capillary pressure. They just retract to certain regions. So to control the drying phase in detail is very important. But then we do a reduction treatment, and we do it at different temperatures. And the higher the temperature, the larger the particles. So this allows you really to tune, in this case, palladium particle size on carbon. I'm not going to in detail how to characterize particle sizes, because there you can give a whole different lecture. But of course, X-ray diffraction is an average method to measure the crystallite size. Electron microscopy is a very good method to visualize and to illustrate the particle size, but it's not so statistically relevant, so you always need to check with another method. And then there are other additional techniques. So for the small ones, XAFs, but also, for instance, XPS can be used. And this is my last slide, really only about preparation, because when I think about it, when I reflect on it, especially if you want to make bimetallic particles, things get even more difficult, specifically with these relatively scalable techniques that we have, because then you would also like to have the two metals equally distributed over the particles that you have. And what you very often see if you use these simple techniques is that you have particles which have a size distribution, but also composition distribution. So if you have two metals, very often some particles contain more one and some more the other. For instance, the larger particles might contain more one metal than the other one. And this is because it's very difficult in all these heating steps and decomposition and phase change steps to control both metals and metal precursors in the same manner. And I'm not going to talk about it in great detail, but in this presentation I will have two examples. And one is palladium copper that I just already showed the preparation a bit, but the other one is nickel copper. And there we used a relatively crude method, so just from nitrates depositing nickel and copper. And this can work relatively well as soon as you have two metals that really like each other and that have more or less the same decomposition chemistry. So in this case, for nickel and copper, it goes reasonably well to have them together, but this is just in specific cases when the metals are pretty alike. On the other hand of the spectrum, you have really nice colloidal techniques, and then you can control everything. Particle size, particle shape, facets, but also the composition can be controlled really well. Another person from our group, Jessie van der Hoeven, will give a presentation, well, a poster about it on Thursday. And then the ones that I love are somewhere in the middle, because we use impregnation methods, so it is relatively scalable, but we try to use all the tricks and all the understanding that we have to get really nice bimetallic samples. This can be complexation by specific ligands, forming a gel so that you have a high viscosity and it does not separate, playing with the charge of the surface, of the particles that you're depositing, of your precursor complexes, and in that way managing to have all of them distributed very uniformly. You might, of course, also use a molecular bimetallic precursor, which is very interesting. And another technique that we like a lot is electroless deposition, because you can first put one metal and just put a monolayer of the second metal in a very controlled manner. This also gives you a very good control over the distribution. So I'm not going to go in detail for all these different techniques, but in this presentation I will use some nickel copper, which is made by a really crude technique, I would say, because they can be derived from a nitrate precursor in the same manner. But I also will use some copper palladium, which is made by a nice colloidal technique, where there's much more control. And in the session after me, Chris Helfrich will give a talk about palladium nickel, and also Hidden Knowlton, another PhD candidate from our group, will give a talk on Friday about silver and gold. Okay, so let me go to two cases. I would like to highlight two examples of bimetallic catalysts. And in both cases, I'll be looking at particle size effects and I'll be looking at composition effects. And I really like to start with the first one, which is the selective hydrogenation of butadiene. And I'm using palladium copper and palladium copper catalysts for that. And this is the work of the PhD candidate Oskar Brandt-Korstius, who just defended his thesis earlier this month. So I don't think I need to introduce to this audience selective hydrogenation. So you could understand many things. Also, CO2 hydrogenation is selective if you make different products. But in this case, we actually mean that we have organic molecules which have different moieties that could be hydrogenated. And what you mean by selective is that actually you'd like to stop halfway. So for instance, if you have a triple bond, you would like to hydrogenate to a single bond, to a double bond, to an olefin, but you would not like to hydrogenate the full way. Or you have nice functional groups, you would like to specifically, for instance, just hydrogenate a double bond, but not the functional group reduce it. So this is used in an enormous amount of reactions. But one of them for which it's used is actually polymers, because you would like to have these ones as polymer precursors on a very large scale. And the trick is really because, of course, if you put hydrogen and high pressure and some heat, you could hydrogenate the full way, and it's very difficult often to stop halfway, and you need specific, very good catalysts to do that. So the type of reactions that we are interested in here is purification of olefins for polymer synthesis. So what you would like to have is the one that have only one double bond left, but you're often starting from a mixture of other things, also with triple bonds or with maybe more than one double bond in a molecule. And you'd not like to retain the one with the triple bonds or the multiple double bonds. Why not? Well, in some cases, they actually poison the catalyst that you have after that to make the polymers. But also if you have a mixture of different things, your polymer quality will go down because you'll get a lot of branching if you have still multiple double bonds. So I love to give this presentation here because this reaction, studying it in the lab, was really inspired by my stay at the Sorbonne Université in Paris with Catherine Louis and Laurent Delannoy. It inspired me to even dare to start, I would say, on this type of hydrogenation reactions. So I'd like to thank them for that. And what do we do? So in our reaction, what we do use as a model reaction, so we have this butadiene, which has two double bonds, which we would like to hydrogenate to have only one bond left. And even more preferably, we would like to have the one butene isomer and not the isomerization to one of the other ones. What we definitely would not like also is to have this one butene being further hydrogenated to butene, But we test this as a model reaction by adding an impressive amount of something which already has a double bond, which is propylene. So this is a test reaction in the sense that we try to have this very low concentration being hydrogenated only once, while there's something else that also would like to be hydrogenated, and it's in a 100-fold excess, and we would like not to make any propane. So it's a very challenging set of test conditions. And it's very much like what you have in real life if you're working with these streams, except for one thing. So also in real life, you have an excess of the product that you'd like to make, and you still would like to have these very small amounts of reactants being hydrogenated. And also the hydrogen ratio is almost the same as you use in a real application. The only thing that we do different is that we work at a lower pressure. So which metals can do this? Well, almost all the hydrogenation reactions can run with almost all of these metals, but there are some differences. So if you look at this group metals here with platinum, palladium, they have relatively strong absorption energies for hydrogen, which means that they're very good hydrogenation catalysts, also nickel is included. But they're very active, and they might be too active to stop the reaction halfway, because they might really prefer to go all the way for the hydrogenation. So they're very active, but not so selective generally if you just leave them unmodified. And the stability is a bit jeopardized because you might form all sorts of oligomers and other things that might deactivate your catalyst very readily. On the other hand, more recently, people have been looking at these metals which were considered sort of inert, like copper and silver and gold, because the hydrogen absorption energy is close to zero, so they have a very low coverage of hydrogen on the surface, and hence a low activity. But the selectivity is potentially very high, which is also related to this low hydrogen coverage. And the stability can be excellent if you handle them well and you prepare them well. So I'll discuss today palladium from this group, copper from this group, and then I'll move to bimetallics. So I like always to first sort of understand the reaction when I try to understand what the catalyst is doing. And one of the ways of understanding a reaction is looking at the reaction order for the different reactants. So in this case, I'm looking here at the reaction orders as a function already of particle size. And one of the reactions, of course, is the hydrogen. And hydrogen has a high reaction order. It's close to 1. What does that mean? It means that there's almost no hydrogen on the surface. It's actually the amount of hydrogen on the surface that is rate limiting. So every time that the hydrogen does absorb on the surface, it's very happy to do something. Then there's a negative reaction order actually in the main reactant, which is butadiene. And that might sound a bit counterintuitive because the more reactant I add, the slower the reaction goes. So that's expressed here. But it's not so counterintuitive. It basically just means that my metal surface is covered with butadiene. It's the one that absorbs most strongly. So basically this whole metal particle is covered in butadiene. And only now and then one of these hydrogen atoms manages to find a place, and then you'll have hydrogenation reaction. So that explains why it is negative, because if I have more, my surface is even more covered, and there's no hydrogen that manages to squeeze in between to do the reaction. And I actually need both of them for the reaction. So butadiene very strongly adsorbed. And then you see here the propylene, and it's less strongly adsorbed than the butadiene. It has a reaction order actually close to 0. It can vary a bit. And that's good, because it means that actually it's the butadiene that is dominant on the surface. It's now and then a hydrogen arriving, and there are very few propylenes there. And also, if there are very few propylenes, there will also be very few butenes remaining on the surface. So this is my picture of the reaction. So it's covered by butadiene. Now and then a hydrogen manages to squeeze a place in between, and then it's hydrogenating. But as soon as it did that, my butene will leave the surface because it's absorbing much less strongly. Good. So we looked at particle size effects. If you look at the particle size effects and the selectivity, it actually goes up with particle size. So very small particles are not the best to have a good selectivity, and this is new. This was not really even known for palladium. And also it's interesting, you see also in the isomers that you make. So the isomers, you'd like to have the 1-butene, but thermodynamically it's the least stable. Thermodynamically, butene would be on top, and then the 2 butenes, and only then the 1-butene. So this is really a kinetic effect. So you absorb the butadiene, you make 1-butene, and immediately it leaves the surface, and it does not come back, because if it comes back, it isomerizes. And you see that this works well for large particles, but for the smaller particles, it starts to mess up. So I get also full hydrogenation, and I get also isomerization. And this we can understand if you look at the turnover frequencies for the two different ones, so the butadiene and here the single alkene. And actually, specifically for propylene or butene, the rate goes up if the particles become smaller. And you can explain that, and it has been explained also nicely with DFT calculations, that if you have these lower coordinated sites that you have in small particles, actually you have such a strong adsorption that you cannot rely on this preferential adsorption of the diolefin anymore. I mean, you have really a mixture of everything adsorbed. Also the ones with only a single double bond, they adsorb relatively strongly on this edge and corner sites. And then they also get hydrogenated. So you need a relatively flat facet to do this reaction well on palladium, and it's also known. Mind, because I showed here very nice selectivities going to 100%, but this is at 10 to 20% conversion, which is very nice for the lab, for the laboratory, but not so nice if you would like to remove all your impurities from a stream. So what is more relevant is to look at the selectivity as a function of conversion, and then you see that on pure palladium it goes down dramatically. So you really get to very low selectivities when you're pushing the conversion to the higher levels. And here you see the particle size. So the largest ones have the highest one, and the small particles really have very low selectivities. I'm making the story about the copper short because it looks very much alike in many different ways. Also there, the selectivity is highest when you go to the larger particles. Can be understood in a similar way. There's also a strong increase in activity when you go to the higher particles. But the main difference with the palladium is that the activity is much, much lower, about 1 million times lower under the same conditions. But the selectivity is much better. And this is probably because this hydrogen even adsorbs less strongly on the copper. So it's really the coverage with the hydrocarbons that determines the selectivity. So we thought, okay, let's combine both. And maybe we can find some nice bimetallic where we have a high activity of palladium and we have a great selectivity of copper. Oh. And here you see the difference. Huh? So this is a logarithmic scale for the activity. It's amazing. And this is a scale for the selectivity. And there have been many reports in literature where it has been called single atom catalysts, which means it's just a dilute alloy of platinum or palladium in another less active metal. And they have been reporting also recently really wonderful results of having single palladium atoms in a larger facet of another metal like copper. So we were very eager to also find these effects. So this is how we prepared the bimetallic particles. And this is a colloidal synthesis. So here we made sure, and we also verified with electron microscopy and elemental analysis, that we really in each of these particles had exactly the composition that we wanted. And we made this whole range of compositions with relatively low palladium loadings. And the crystalline size and the particle size is about 5 to 7 nanometer for all catalysts. And we first made them as colloids, and then we deposited on a carbon support. And it's usually quite difficult to deposit colloids well on a support without any change. But actually carbon supports are one of the best ones because these ligands very nicely interact with the carbon. So you do get a uniform distribution of your metal particles. This is what we found in activity. And we were a bit disappointed, honestly, but still it's interesting. So this is the turnover frequency. Here you see the one which is of pure palladium. And then with this relatively low loading, so it's up to about 12% of palladium in the copper, we found a sort of plateau between 3 and 12% or even higher. And then we found if you put less palladium that it's even less active. And just to make sure, this is the activity plotted per palladium atom. So it's not a turnover frequency per total atom that we expect at the surface, but it's per palladium atom that we expect at the surface. And if there would be any synergistic effects, I actually would like to see the palladium even surpassing my pure palladium. It does not at all. In terms of activity, it's actually about 1 order of magnitude slower than the palladium would be in a pure palladium. And then you also see these 2 regions. There's a sort of plateau of a wide composition range. And then if you have little palladium, then actually it gets even much less active per palladium atom. But this is what we measure. And if you look at the selectivity, So you can, of course, look at different conversions. It's not so fair to look at 15% conversion, but if you push it completely to 90% conversion, you see your selectivity for copper is the highest. It goes down if you add a bit of palladium, but it actually stabilizes also around this 3% of palladium, and it's not so bad. And mind that I put here selectivities of 80%, but it means that my hydrogen in 80% of the cases is used for the reaction that I'd like to use it for. But mind that I have a 100% excess of the reactant that I would not like to hydrogenate. So in fact, it means I have 98 or 99% of selectivity if I just look at all the reactants coming in, that it's picking the right ones. But this is the most severe way in which we plot it. So at high conversions, this is the selectivity that you get for your hydrogen, so it's a hydrogen selectivity. But also here, I see no wonderful synergistic effects. And we tried to understand what was happening. And first of all, you see this plateau, which is interesting. And why do we see this trend? And with XAFs, we actually found that if you go to the very low palladium loadings, you probably have really single palladium atoms in a sea of copper. And if you go to the somewhat higher one, they start to preferentially cluster. And you always have about 3 or 4 of them next to each other. So they form this sort of small islands in the metal alloy, which explain why you have a trend where it's pretty constant. So that's a geometric effect, but there's also an electronic effect. So we also do see with xenes some charge transfer, some electron density transfer from the copper to the palladium. And that probably might explain or help to explain also why the activity per palladium, even if you have a small ensemble with 3 or 4 of these atoms, is lower, is about 1 order of magnitude lower than it is for the pure one. Having said that, of course, we were slightly disappointed because there were all these wonderful reports, but it's difficult also to see sometimes if people use the right reference. So they put 2 metals and then they put a wonderful thing in the middle. But you also have to be very careful in reading the paper and seeing whether these references are really the same. And it's not, for instance, partially oxidized copper, or it's palladium with a totally different type of properties. Having said that, I can also make life a bit positive. I mean, we are able to choose here to have a relatively good selectivity and to boost the activity of the copper by adding only a few % of palladium. So it's a very effective way of using the palladium. So in total, if you sum up particle size effects, composition effects, and I did not talk about doping with other elements, but you can use this to actually kill the isomerization step, we are able to better understand how to make a good catalyst for this reaction. And that brings me to the second topic that I'd like to discuss, which is shifting gears, nickel-copper for methane decomposition. And this is the work of Suzanne Schoemaker, who also defended last month her PhD thesis. But I also would like to acknowledge Petra DE JONGH, who was actually the one that suggested that this would be a great reaction to look at in detail in an electron microscope. So I will introduce the reaction to you, then I'll go again to particle size effects and to composition effects. It's an interesting reaction. So what you can do if you have methane, you can decompose it to hydrogen and carbon. And in principle, this means that you use a fossil fuel, but you use it in a way where you do not emit any CO2 because you can use your hydrogen as a clean fuel. And you can grow all sorts of carbon nanostructures over catalysts, which are typically nickel, iron, or copper. Nickel is the one that you see here. It's growing usually carbon nanofibers. Copper, for instance, can be used to grow graphene, so it does not really propagate these larger ones. And iron can also be used for either carbon nanotubes or carbon nanofibers. The reaction has been studied in the past, and interestingly, then it was about the carbon. So the source was often not methane, it was, for instance, syngas or another hydrocarbon, and they were interested to make nice carbon structures. Nowadays, the focus has shifted because now actually the interest is in the hydrogen as a clean fuel and using methane without burning it to CO2. But there's a lot of knowledge from the growth mechanism, for instance. So you have a metal particle on a support, but it might either stay there and just start to form the carbon being launched, like here, like forming a tower, or the particle itself might be launched as a sort of rocket by the carbon that's actually growing, and this we call base growth and tip growth. And there's been a very seminal work in electron microscope, and this has been the work of Stig Helveg when he was still at Helder Tupse. where he visualized a single particle actually growing one of these carbon nanofibers. And this is part of the inspiration that we used. So what will we add to this? Well, two things. We will do studies of ensembles of many individual nanoparticles at the same time in the electron microscope. And we couple them directly to macroscopic studies in the reactor. So we'll really be checking the kinetics, because in a microscope you might see many different things that you'll never see in real life in a reactor. So we really try to make the bridge between the two. And nowadays we're able to look at many particles at the same time, not just focusing on one, and studying them really in a catalytic reactor at 1 bar instead of very low pressure. So this is actually done at very, very low pressures because it's differentially pumped microscope. So the catalysts, either they're just nickel, they're just made by impregnation from a nitrate solution. We have a heat treatment, and this is all very crucial for having very nice particles, but I won't talk about it. What's maybe interesting to know is that we started out making a nice series of particle sizes, 1, 2, 3, 4, 5, etc., nanometer, which turned out to be completely useless because under reaction conditions, these particles grow to a certain size. And you usually see them growing to at least about 8 nanometer, even if you had a very nice size distribution before. So that's what you see before reaction actually means already at the reaction temperature. And at 500 degrees, these particles become relatively mobile and they grow to about 8 nanometer. We also make this nickel copper, and actually it is, as I said, very easy because nickel and copper really match well, both in terms of the chemistry for the impregnation and the heat treatment, but also they're very easily mixable metals over the full range. So we followed it in 2 ways. One thing is that we followed it in situ, or I could even say operando, just gravimetrically, because you're growing carbon, and it means that your sample becomes more heavy. So we just are measuring the weight, and we're feeding methane, and we're measuring the weight of carbon that is being formed. And we couple that to experiments in the electron microscope. And in the electron microscope, we have the same feed and the same temperature. We try to mimic the same conditions, but we have this reactor cell inside the microscope, and with the electrons, we're actually probing what is happening on a very small scale. So let me give you some feeling for the system. So what you see here is the carbon yield. So this is measured gravimetrically as a function of time. And you can do that, for instance, at different temperatures. And what you see if you go to a very low temperature, like 450, growth is very slow, but it continues for a very long time. If you go to a very high temperature, like 600, it's like a burst of carbon, but it also stops very, very rapidly. So of course, what you'd like to have at the end is an optimum amount of, or the maximum amount of carbon. And the optimum is then somewhere in between, because you get the maximum when you take a sort of intermediate temperature. And another thing is adding some copper to the nickel. And this is really spectacular. So with the nickel, the growth stops very, very soon. And this is actually because the nickel, it grows carbon, but it also grows amorphous carbon. And the poor nanoparticle is actually at some point encapsulating itself. So it's excreting carbon on all sides. And it means it's just blocking its own access to the reactants, which are in the gas phase, and it stops growing. And if you add a little bit of copper to that, it helps a lot. So it keeps the surface free of this amorphous carbon, and it makes that it's still growing. And this was already known. And that means that in most samples, we put at least a little bit of copper. And it also means, for instance, in temperature, you'd like to have a balance, you have an optimum, because at the real low temperatures, it's actually the methane composition that is rate limiting. So you have a reaction order of about 1 in methane. So you just don't have enough carbon going to the place where you can grow the carbon. But if you go to very high temperatures, it's actually the carbon formation that cannot keep up anymore. So you get a much higher reaction order there. But then you also form everywhere carbon, because your nice crystalline carbon cannot keep up and your particle gets encapsulated. And the optimum is in the middle. So now we go to the electron microscope and we studied it under exactly the same conditions. And a few things are wonderful here. And one is that normally, if you would like to have 10 different particle sizes, you need to have 10 separate experiments. And if you have 100 particle sizes, you need 100 experiments. Here you can just throw in a sample that is not extremely well defined in particle size, I would almost say on purpose, because it means at the same time you can look at all different particle sizes that you see in the sample. So what you see here is graphene sheets And on top of them, you see the dark dots, and these are the metal particles. And then we will put some methane gas on top of it, and you'll see from these particles, you'll see the carbon growing. And it's really like a can of worms, as our postdoc called it when he first saw it. So you see all these events happening at the same time. You see different growth modes. You see carbon nanotubes. You see carbon nanofibers. You see encapsulation, and some of them stop growing because they're deactivated. You can also see that happening. Some split. So you see here one that forms multiple. So it's getting caught, and it's partially encapsulated, escapes in another direction. You see some of these particles changing shapes. You see some of them faceted. You see some of them round. So it's an enormous variety of data that you just see in one sample, just looking at it for, well, this is like 20 minutes maybe at most. And this is at 550 degrees Celsius. So I found this really, really amazing. And the experiment itself is not so long. Well, it took us 2.5 years to get this experiment working in an electron microscope. But once you can do it, it doesn't take so long. But you can also imagine that the analysis of this data is like horrendous, because you have all this different data, and now you would like to segment and analyze quantitatively per particle what it's actually doing. So to line out a few things, so here's a zoom in, where you can see a bit better particle size effects. And you see, for instance, the large ones faceted here and growing very, very slowly. There's very well-defined fibers. You see also the smaller ones, they're growing faster at any given temperature. And they're actually forming something which is hollow. In this case, it's even a nanotube. So you can really immediately see, as a function of particle size, initially, the small ones are very fast. But they also deactivate fastest, so after a while, you actually only have the large ones that are still growing. There's this really speedy Gonzalez type of particles, and you also see at some point it gets very full. This is also a practical limitation of the process. So particle size effects, we can measure them, and can also correlate the rate that we see in electron microscope to the kinetics in the reactor. And this is really, I think, very unique. Then I go to composition, so it's just 2 slides. We add some copper to the nickel. So they all have a similar size, but they just have a varying composition in nickel and copper. And we saw that the initial growth rate is affected, so it actually goes down when you put in more copper. But also the total yield, so how much carbon you can grow at the end, goes up a lot if you add about 30% of copper. And we really were struggling to understand this. So copper keeps the surface a bit free of the amorphous carbon, so it helps to the deactivation. Because it's not such a good nucleation site for this amorphous carbon as the nickel is. But there must have been something else to it, because we're operating at temperatures where also this carbon secretion is really crucial. And what we actually saw is that the copper changes the growth rate of these carbon fibers. So with only nickel, we have a growth rate which actually goes all over the place. So it's not growing, and it's growing very fast, and it's not growing, and it's growing very fast. That's what you see here. It's what we call stuttering growth. So you see it escapes, it does something, and then it stops again. And it escapes, and it does something. And so this is really a continuous dynamic process of partial encapsulation and escape, and partial encapsulation and escape of the particle. And if you add some copper, you get a much more continuous growth, what you see here. And actually also the particle is much more spherical. It looks almost liquid, and it very continuously, with a continuous rate, will continue to grow the carbon. And we correlated this to the solubility of the carbon. So actually the problem is that you decompose methane, but only on one side you're growing a nice carbon nanofiber. And you need to transport your carbon through the metal nanoparticle to this site. And this depends on the solubility of the carbon. And the solubility of the carbon in nickel actually goes down when you add some copper, but for a long time it stays more or less at the same level. And then just above 30% it goes dramatically down. So what we think is that a bit of copper helps, actually, because you have a better solubility, you have less deactivation, but at some point your solubility becomes so low that, again, you decompose methane and it forms carbon there, and then it stops growing. So with that, I would like to conclude this part. So it's a complex interplay, because you need to decompose methane on the surface, it needs to diffuse, and you'd like to form these nice structures. But playing with particle size, composition, temperature, of course also the feed and the support I didn't even mention. And you can try to really maximize the yield of this process. And coupling macroscopic to nanoscopic measurements, I think, is really a great tool to understand on a very small level what's happening. So I would like to acknowledge all these different people and also the different funders, and I'd like to thank you for your attention.